This is part 3 of the lecture, Non-iterative and Iterative Image Reconstruction Methods. Here now we're going to move on to the case of more general linear mappings, in other words, linear shift variant systems, and then look again at Tikhonov regularization, as well as doing direct inverses via SVD, the singular value decomposition. So far then, we've been dealing with convolution, LSI, linear shift invariant systems. Fourier transform diagonalizes those systems, allowing easy reconstruction methods. And as said, we're now going to move on to the LSV context. So 3D PET is an example of a linear shift variant system. You'll recall that we've been dealing with LSI for back projected PET data. That would be, by analogy, if we imagine this as a cross-section through a PET scanner here, this is just a ring of detectors, and if we had a point source in the middle there, if we back project data, we get this kind of 1 over r point spread function that we've been dealing with, that we've seen in previous slides. And crudely, if we were to move it towards the edge, it would more or less, this is a bit of an extreme position here, more or less stay as a shift invariant response function. However, if you look down the axis of the PET scanner, so this is a transverse cross-section of the scanner in these two cases here. If you were to look into the plane of the screen here, we would have a whole stack of these rings of detectors. And you can see a point source in the middle there has quite an axial wide angle of acceptance. And so back projecting data would give quite a large sized point spread function. Whereas if the point source were to be located at the ends of the scanner, you can see that that axial angle is much, much smaller. And so we've clearly got a very shift variant 3D point spread function if we back project PET data. Therefore, Fourier really will not be of direct use in this context unless you use very special tricks and so on, which people have tried, but it's not very elegant, and you end up needing to reject data to make the system shift invariant again. So we do need more general methods. Here I'm just showing the example of that well-known point spread function that you've been looking at in previous videos. And here I'm just illustrating it again. That would be, for example, the lines of response, just an example, back-to-back photon pairs that would be back projected, for example, to give that kind of back projected point spread function. For the 2D case, if we imagine imagine you'd have a ring of detectors just there where those red lines are. And then what I'm trying to show is that with this axial case, I'm trying to show back-to-back photon pairs that kind of go deep into the scanner. Obviously, we have isotropic emission of back-to-back photon pairs, and plenty of them go into the kind of fully 3D geometry of the scanner. Anyway, all that to say, 3D PET is linear shift variant, and so the convolution methods we've been looking at would not work. So what do we do? Well, we could stay then with the idea of a back projected image, just back projecting those red lines, those photon pairs we detect, and get a back projected image G. And then what we'd be doing is looking for an image, a reconstructed image F, strictly an object representation vector of parameters, which when mapped through H can match that back projected image. So this H is very much like what we've seen before with the convolution, where it had the point spread function in each column, but it was always the same point spread function. Now we will need a unique point spread function. Obviously each column is a vector which just when reformatted, forms a fully 3D image of a point response function, just as G is a vector that holds a 3D image as well. What we now need is to find, therefore, the vector F, which when mapped through that matrix, holding all the unique point spread functions for all the possible positions in the field of view, needs to match the measured data, the measured back projected data G. And so this is a formulation of the least squares problem for the linear shift variant case. So it should look familiar from what we've seen before, and we're just saying that FLS is the argument vector F of parameters representing the object. Notice here we're no longer in the Fourier domain like we were before. Now we're kind of right back to basic matrix vector. The F that when plugged into here and goes through that linear shift variant mapping needs to best fit in a least squares sense, minimize L2 norm distance squared, needs to best fit the back projected image. So if we put that into subscript notation, what I've done is just spell out the L2 norm there and just spell out matrix vector multiplication here, just showing a subscript notation, because that's going to make it much easier now to go ahead and find the values f that are going to minimize that objective function. In fact, that's why I've called it OLS here, the least squares objective, but as you know before, I've used L for loss function, could use C for cost function, whatever your preferred notation is. So here I've done a partial derivative with respect to one of the parameters in that vector. So that's, for example, one element fj out of all the elements being considered here. So I'm summing over, in fact here the matrix vector operation is summing over 1 to capital J elements in that input vector, which are forward modeled to deliver a predicted back projected image. And so I'm just picking one of those for the partial derivative, and then performing the partial derivative on that. So therefore the 2 comes down the front, cancels that 1/2, which is why it was kind of put there in the first place in anticipation of differentiation. And then we just simply multiply by the derivative of this term, this expression rather, with respect to a particular element of the vector, so fj. And so one of the terms there will contain fj, because this is b runs from 1 to capital J, and one of them will be j, fj. And so what we've got then is the 2's come down the front, we've kept that expression, and then we're multiplying by the derivative of this. And so one of these terms, as mentioned, will be hij fj, and so therefore the coefficient of fj, in order to get the derivative, is just the hij, so that just comes here, and obviously we keep that outer summation there as well, that stays in place. So if we follow that through, we're going to set the partial derivative to 0, and the moment we do that, we no longer have a kind of a function here of some fj. Now we're saying that for this to be true, that f that's left behind in here must be the least squares estimate. So notice, even though I did the partial derivative with respect to fj, because of this summation in here, which we didn't have before with the Fourier case of the diagonalization, we had a very trivial mapping. Now we are still dealing with all of the elements in the vector f. Okay, they all appear here. So let's now work that through. So just rearranging, this is sigma I, hij, gi, which I've just put on the left-hand side there. And then a minus here gives a plus for the sigma I, hij, and then this term just stays the same. So hopefully you can begin to get quite skilled at recognizing matrix vector notation here. I hope, for example, here you'd recognize, obviously it's come straight from here anyway, you'd recognize that as just nothing more than the matrix H operating on the vector F. And so what that means is it's effectively doing, in quotes, a spatially variant convolution. Obviously it's not convolution, but it can sometimes help to think of it that way, where you're just substituting each point source in F with the particular point spread function according to the location of that point source. So it's kind of just doing the prediction of the back projected image with the space variance built in. And then that's going to give effectively a back projected image. And then that's operated on by the matrix H again, but look at the order of summation. Here we're doing the conventional matrix vector multiplication, but here look, we're summing over the first index there, and that corresponds to using H transpose on that vector. And so you notice on the left hand side again it's a summation over this first index here, and this corresponds to H transpose operating on G. So in matrix vector notation then we've got H transpose G needs to equal H transpose H F LS, and the FLS that satisfies that equation will be the least squares estimate for this more general linear mapping H. So that's the direct least squares solution. These are also known as the normal equations. It's a standard known solution for the least squares problem. Here it's just rearranged, but really you can also write it with H transpose H minus 1 in front of that And I've put here a little point of comparison with what we did with the diagonalization of the Fourier method. You may recall we were dealing with that expression and just showing that there's an obvious similarity there. And there I've just written it now with the -1 on this H transpose H. So in other words, we need to invert that matrix, assuming it is invertible, which obviously could be found by checking the condition number and so on. Yeah, so that's the least squares estimate. Now for a more general matrix H. So let's take a look at what it does with those previous back projected images that we were working with. So if I do a noise-free implementation, this was done in MATLAB, of that exact expression you just saw, the reconstruction quality, when you first do this kind of thing, is surprisingly good. I mean, it's virtually pixel perfect. That looks identical to the phantom that I'd put into this simulation. And if we compare that to what we did with the Fourier-based reconstruction, it was far from perfect. I mentioned before why that was. You know, there are all kinds of approximations. For example, the point spread function is not even shift invariant, strictly speaking, and you've got edge effects in there as well, because the kernel is not fully defined. You'd normally need to back project into a much larger array in order to cater for the full point spread function for deconvolution. But anyway, if you do it this way, look at the how clean that reconstruction is. A very nice least squares result, in the absence of noise, of course. The moment you put the noise in there, this is a noisy back projected image, then the inverse gives a pretty bad result. So noise is a problem. What are we going to do? Well, let's try Tikhonov regularization. So this is just like what we saw before, but now regularized least squares, or penalized least squares. This is known as a penalty. And you can see that's all we've done is we've just added on the L2 norm squared of the vector that is the solution that we're looking for. Because you'll notice in that previous slide, when there was noise, we basically had an exploding solution that basically meant the rest of the information wasn't really visible. So this acts as a penalty for large valued solutions, because that will inhibit finding Fs that minimize that. Because if this fits well to that but causes a large F, then that won't be an acceptable solution. That won't be a minimum for this regularized objective function. Okay, I mean, we've talked about that in the previous video in the context of Tikhonov regularization for the Fourier-based inversion. Okay, there it is in subscript notation. I've already discussed this expression. That's the data fidelity, if you like. And now we just have that Tikhonov expression on the right-hand side. Again, same process, just partial derivative with respect to one of the vector values. And we get the same expression that we had before, but now we just have this additional term here, which is just the derivative with respect to fj. And so obviously just one of those terms in that summation is fj. And so that's why the 2 comes down the front, but obviously cancels actually with the half that was put in front of the objective function. And so we're just left with lambda fj. Right, and then again we do what we did before. That's exactly the same working as what we did before there, but we just again now have that Tikhonov term there, if you like, for the regularized least squares solution. And so because I've set the derivative to 0, that's why I've got RLS, regularized least squares estimate. So what I've done there is just interpret as we did before. You should recognize that as H transpose G. This is HF, and that's H transpose operating on HF. And that's obviously just F there. So bear all that in mind, and that's how we get to that expression at the top of the screen. Okay, and then we can now write the direct inverse of that to solve for F. Then obviously we just factor out H transpose H plus lambda, and then we need an identity matrix in there as well, because we're just factoring out FRLS, and sorry, so that was then put on the other side of the equation to leave FRLS is equal to H transpose H plus lambda I inverse multiplied by that term there, okay? Because obviously this was factorized there and then put down the denominator there, which effectively meant we needed the inverse, which is what we're seeing here. Okay, so there it is again, just written in terms of the denominator. And so this is Tikhonov regularization again. And what we see is then that we're adding on a scaled identity matrix, there it is there, lambda I, before inversion. So if you think about that, imagine that actually had a zero eigenvalue or a zero singular value. Then it would not be invertible. But if we just add on lambda I is the identity matrix, just 1 all the way down the diagonal, scaled by the penalty strength, the regularization strength lambda, then that's going to have a sort of a safety net all the way down the diagonal, and it's certainly going to make this now, I would imagine anyway, an invertible matrix. And so, we've just changed the condition number. If we look at consider the condition number as the max to min of the singular values of HTH. But then, of course, now we're considering the condition number of that new entire matrix that we're now inverting. Okay, right, so let's move on to the next slide. I think what I meant there was that decreases the condition number of the matrix being inverted. So I must correct that. And so as a point of comparison again, this compares in a very obvious way with the Tikhonov-based regularization for the direct Fourier approach. So let's look at the results of doing that. This is what we already saw before. That was the back projected image, which you'll remember was G is equal to HF. That's just the model of the back projected image given a candidate true object F. And so here we didn't know what F was, but we measured G. And then we just solve the least squares problem, and we get the least squares solution just being given by this operating on the back projected image G. And there we have our rather nice reconstruction again. Now if we were to do the regularized solution by adding on that lambda I to H transpose H before using the inverse, then you can see that's done pretty much what we saw with the Fourier case, where it's caused a reduced strength of recovery of the vector F. Okay, this is like a slightly more blurred version of what it should be. Okay, so now if we really had noise-free data, then we wouldn't do that. We might as well just go ahead with this clean direct inversion approach. But in reality, data are noisy, and that's why we looked at the regularized solution, remember? And so here is the noisy result. But if we put in a lambda here, given the scaling of these matrices, a lambda of 100 seemed to give a fairly reasonable result. Obviously a lot of noise in there, but compared to the case with no regularization, this is a clear benefit. And I refer you again to previous discussions regarding how you might choose lambda. But just to add again, though it is largely empirical most of the time. Okay, so those are sort of direct least squares and regularized least squares solutions, estimates. Now let's take a look at what the singular value decomposition can offer to us. I mean, what's maybe not so obvious about those previous methods, if I just flick back a slide, is that we're adding on this lambda I, okay, like a diagonal, to a matrix that's clearly not diagonal. And this is not the most obvious construct. Recall also that I was comparing this to the direct Fourier inversion, where we really did have a diagonal matrix and we really were dealing with just, like with like. We were kind of doing an offset just on a diagonal compared to the inverse of the transfer function, which also sat on a diagonal. Whereas this is just like it's somehow, it's fine, it's a correct solution to the regularized least squares problem, but it's not so intuitive as to how we would regularize in that way. Whereas if we do a singular value decomposition, we can now diagonalize the matrix, even though it's still a linear shift variant matrix. We can diagonalize it, and then all that kind of nice analysis that we did for the Fourier-based inversion, we can now do for the linear shift variant case as well. So singular value decomposition is a very powerful method. So what it does is it takes a matrix A and decomposes it into three matrices. And so by direct analogy, what we were seeing before was that a convolution matrix H was being diagonalized by a Fourier transform and then a diagonal matrix which held the transfer function down the diagonal, and then an inverse Fourier transform. And the singular value decomposition just generalizes that concept of an orthogonal matrix of right-hand singular vectors, that's what they're called, singular vectors, and then a left-hand singular vector matrix here, L, and then the diagonal matrix is that matrix sigma. So what I did in MATLAB was deliberately set A to be a circulant convolution matrix, just to show what SVD does for a case where we know what it should do. So let's take a look at what MATLAB did for that matrix when I did an SVD on it. Here now was the matrix of right-hand singular vectors, and they should all look a bit familiar to you, I hope. They certainly look quite sinusoidal to me. This is the matrix of singular values, and you can see the familiar trait of decaying singular values, just like we had the decaying modulation transfer function in all the previous videos that we've done on back project then filter. And then we have the left-hand singular vectors. And again, they nicely look like they are columns of Fourier-like basis functions, which is analogous to the discrete inverse Fourier transform. So doing an SVD on a circulant matrix is delivering visually something that we certainly expect. Obviously, there could be different phase shifts in these sinusoids compared to the actual discrete Fourier transform and discrete inverse Fourier transform, but nonetheless you see that it's very much latching on to what looks like a Fourier-based solution. So here I'm just visualizing some of the 5 of the left-hand singular vectors, 5 of the right-hand singular vectors, and then another 4 of them over here. And you can clearly see that they are sinusoidal functions, so as would be expected for a circulant matrix, for a convolution matrix. And so that means, life is now easy again after diagonalization. We can do an inverse, a pseudo-inverse, via singular value decomposition. So all we do then is A minus 1 and say, well, that's L sigma R star, conjugate transpose of the right-hand singular vectors matrix, inverted. And so obviously we need the singular values in sigma to all be greater than 0 in order to be able to do this inverse, or at least not 0, I should say, in order to do this. But if there are zeros in there, then we know where the problem lies, and we can take appropriate action. So that's the great clarity that you get with an SVD. So just by doing basic matrix arithmetic here, the inverse on that means you take R star, invert it. It's an orthogonal matrix, so R star just becomes R, so it's just the conjugate transpose here. Sigma is diagonal. So if it's R star, then I should be saying unitary rather than orthogonal. And then sigma minus 1 is obvious, it's just the reciprocal of the diagonal elements, and then L star is just the conjugate transpose of L. So as mentioned here then, the inverse of the singular values, that can be viewed in exactly the same kind of way that we were looking at the modulation transfer function and its inverse when we looked at length at the Fourier-based inverse. So hopefully you can see the value of really understanding very well that simple case of direct Fourier inversion for the kind of deconvolution-based approach. If you understand that one really well, then that understanding will follow through very naturally, perhaps to a case that's not so immediately obvious. So when we do that inverse, we can do all the usual kind of tricks. We can add an offset to the inverse of along the diagonal of that singular value matrix. You can do a kind of Hamming window. You can truncate, but obviously you've got to be careful with abrupt truncations, just like you have to be careful in the Fourier domain with abrupt truncations, because you get ringing effects if you suddenly cut off use of some of the singular vectors, or in the Fourier case, some of the eigenvectors, some of the Fourier basis vectors, so you do need to be careful with sudden truncation. Okay, so that's all very well and good, but I have to say to you, I have not yet ever run a pseudo-inverse for 3D PET data. Probably a number of reasons. Well, first of all, it's the wrong noise model. We have Poisson noise in PET, so I'll be talking you through the correct noise model for PET and how we do statistical reconstruction. That's one reason, the wrong noise model, but that wouldn't stop me. I'd still like to try it anyway. But the reason I haven't done it is as follows. You're going to need that matrix, whether it's H, whether it's A, whatever the notation, you're going to need that in memory, or to some extent certainly in memory, in order to calculate its inverse or its SVD. I know there are various computational tricks out there, but I'm not yet aware of any that can really handle the kind of size of matrix H that we need to deal with for a practical 3D PET scanner, or indeed any real practical 3D imaging system. I'm constantly using the example of PET, but the concepts that I'm teaching here are quite general to inverse problems. In later lectures we'll get to some of the very specifics of PET imaging, but here hopefully you'll appreciate these are general inverse problems for medical imaging. And you can see here that this, for a 3D image, okay, I am using an example of PET again here though, where we have, for example, for the PET-MR scanner, we would have 344 by 344 voxels by 128. So that'd be the number of voxels in a 3D image. And so we need as many columns to that matrix as we have voxels in the image. And then we need as many rows as well. So, we're talking well over 1 trillion values to store that matrix H in memory. So this is really prohibitive for using these direct methods. And so that's a major motivator, but not the only motivator, for using iterative methods, as iterative reconstruction methods often only need to access rows or columns of the overall system matrix. And you can often calculate those only as you need them, so you don't have to store the matrix in memory. And the other reason is that iterative methods allow us to get out of the simplicity of least squares. As you would have seen in an earlier video, least squares is very much oriented around a Gaussian noise model, but for PET data we deal with Poisson noise, and so least squares isn't really what we want anyway. So two strong reasons for us to now move on to iterative image reconstruction methods. Okay, and so the next lecture in this series will indeed just start on the topic of iterative reconstruction by covering the very important topic of system modeling. Thanks for listening.